Well, now under our belt, we have logic to do Gaussian elimination and do so in a safe and stable manner. What we have missed along the way, though, is the fact that we are being a bit inefficient in how we're doing partial pivoting or scaled pivoting. So what's the problem? Well, the problem is that when we need to swap rows, we literally do it. We take all the values out of one row and replace the first row's values, and we take the safely stored values out of the first row and put it in the second. That's a lot of work for the computer to do, and there's a better way to go called linked lists. So that'll be our first topic in the session. The second topic will be understanding how to count the cost associated with doing any computational algorithm, and we will be applying that to solving our linear systems. So let's start with linked lists. It is a very commonly used approach which has applicability here and many other algorithms as well. It's a way for us to avoid moving the rows in favor of moving an index. We are following the text starting on page 87 in case you'd like to see where that is in your book. And in this section, we are going to be introducing the idea of putting a new indexed array to keep track of the pivot location or the pivot rows and columns. So this approach, as I mentioned earlier, is called a linked list. It has a wide application. This is just one of many. The basic philosophy is to move an address to a row rather than to move the row itself. The row is physically stored on an array, and rather than moving the contents around from row to row, we will leave the contents alone. We'll never move it. What we'll do instead is come up with a more abstract or a virtual location for that row, and we will work with that virtual location rather than the physical location itself. So before doing any row reduction, we need to set it up, and we will do that using an integer array. This is MATLAB code that would accomplish defining an array called link, LNK, and it would fill that array with n integers, starting with 1 and working sequentially up to n. That will be what we will manipulate rather than manipulating the data. So the link array will do the following. If we are interested to find row k, we will physically find it at link of k. So our algorithm says swap row k with row j. To find row k, we will physically be storing it somewhere else, and it will be stored in link of k. Let's see how that develops. Let's say that you've started off your algorithm, and let's suppose you're at the beginning and link is just 1 through n. And you decide that you need to swap rows k and row Lmax. So the reason I'm using the term Lmax is if I am looking for the row, say for column 1, that produces a maximum value, perhaps because I'm using partial pivoting, then I will call that Lmax. Or I might do the same thing in scaled pivoting. If I am looking for the scaled maximum, when I find it, I will call it Lmax. One way or the other, I have a row number that is a candidate to be moved. I'd like to interchange it with row k, and this is how I would do it. I would implement the same logic that I used when I literally moved cells around between two different rows. This time, however, I am moving the value of link. So I'm going to logical location k, and I'm pulling out the physical location that's stored there and storing it in a temporary variable. Then I will update the physical location of k in my link array using the value that's in Lmax, and then when I come back to update Lmax, I'll take that retrieved value and swap it. There is no difference in this logic between the swapping that we did between two values in two different rows when we swapped the actual A values themselves. The real difference is we had to do it over and over again for each column. Here, we only need to do it once because we are moving the address of the row rather than the physical row itself. So we do not move the rows, we only move the addresses. Now that gives us another job when we're accessing the array. We're used to accessing the array using the physical row location and the physical column location. We can still keep using the same physical column location, but when we extract the value, we have to remember that when we want the value, we're going after a logical row I, which happens to be physically stored at link of I. And we have to do the same thing with the B. So we will be looking for the value of B at logical row I, but it will be stored physically at B of link of I. Okay, let's try it. You'll need to introduce in this new code our linked list that will go from 1 to n, and then we will be swapping the row indices rather than swapping the actual data, but the logic will be identical. We'll do this on the triangularization process without actually moving the rows, so you have to get that portion of the code that was in there out and replace it, strategically put, with this linked list array. Continue using a2.xls. We're going to try to solve this using the same data. Your result should be the same as homework 2.2b, but your A matrix and your B matrix won't look the same. So I will be checking your A matrix and your B vector to make sure they are correct. Make sure you adapt your code to construct the residual vector using the linked list. Make sure that you do all the normal commenting and indenting and all the normal care it takes with writing it. So there's your homework. Okay, so with that, let's go to the second goal for today, and that is to count the processing cost associated with an algorithm. The method that we're going to use applies to any algorithm you want. We're just going to apply it to the back substitution algorithm that we already introduced. If you wanted to count the execution cost associated with an algorithm, we generally do that by counting floating point operations. So we literally go through each division and say multiplication or subtraction, and we count each as having cost 1. Now there are two ways to go about this. You can literally stick a counter in the code. So I'm creating an integer variable called nf and initializing it to 1 because I found my first division. Every time I find a floating point arithmetic operation, I add to the cost. So here there are two floating point operations, subtraction and multiplication. Therefore I could increment my counter by 2. And I finally have one more down here, so I would increment my counter by 1. If I literally stuck the code in there to do that, what would come out the bottom would be the number of floating point operations I did in this code. That's one way to do it. There's a better way to do it, and that is to do it theoretically. I can literally write a formula that involves sums of every time I produce some arithmetic computation. So to explain that, I'm just going to stick it up there. It looks kind of ugly, but it's really not as bad as it looks. I simply go through this code, and every time I find a floating point operation, I add a counter to my formula. So I start off with a 1 for this initial floating point operation. If I come across any kind of a loop, whether it's a for loop or a while loop, doesn't matter, I determine how many times that for loop will pass through the algorithm. In this case, our sum is going from n-1 to 1. And I want to capture all the cost in terms of floating point operations in the entire nested set of code that is inside of this for and end loop. Now when I do that, I turn this for loop into a sum. Here's my sum over here that's accounting for the for loop. Now you'll notice I'm summing from I equals 1 to n-1, but my loop is going from n-1 down to 1. That doesn't make any difference because addition is commutative, so you can add in any order you want, and this just looks nicer to me, so I'm going to add from bottom to top. Now inside that sum, I have to look now for either another sum or I have to look for a computation. The next thing that happens is another for loop. So in this for loop, I am going to have to build another sum that goes from I plus 1 to n. And that is this nested sum, j equals I plus 1 to n. Since that ends the nesting of the loops, I ask how much computation is going on. Well, there are two arithmetic operations, so I put in the number 2. And that summation simply adds up the number 2 as many times as necessary as dictated by those indices. There is one more division, and so we have to add it up after this sum is over, but inside the outer sum, since it's inside this entire outer loop. Let's see if we can break this thing down. One question to ask is, what is the sum from I equals 1 to n? Well, the I plus 1 makes it a little complicated, but if you imagine you were just summing from 1 to n, you would say I'm adding up 2 n times. So that would be 2 times n. You take the upper index minus the lower index, add 1, and that's the number of times that summation occurs. Now the complication we have here is we're adding from I plus 1 to n rather than from 1 to n. But we do exactly the same thing. N minus I plus 1 plus 1. There it is. N minus I plus 1 plus 1. Okay, so that is the number of times I'm doing this particular summation. Let's not forget this 1 is also contained in the sum, and therefore I need to add it up from 1 to n minus 1 times also, which is just n minus 1. This sum here becomes n minus 1. If I reduce algebraically this expression, I end up with n minus I minus 1 plus 1, which turns into just n minus I. The whole thing's multiplied by 2, at least the summation is, and I have my initial 1. How do I add up this sum? Well, actually, it'd be easier if I recognize that we're just adding backwards from n minus 1 down to 1. Well, let's just add them backwards. It would just be easier because all we're really doing is adding up I from 1 to n minus 1. So this expression and those expressions are identical. It's just a little simpler. But I have a formula for this. If you remember from the beginning part of this class, we were adding up integers, and we know how to add up the first n integers. That was n times n plus 1 over 2. Well, now we're adding up the first n minus 1 integers, so that must be n minus 1 times n over 2. So we can replace that summation with that formula that we're familiar with. And most conveniently, these 2's are going to cancel. So this expression is going to result in n squared minus n. By the time you add that last n in there, these 2 cancel out. And very simply, the total number of computations is n squared. We're going to give this algorithm a name. We're going to call it an order of n squared algorithm. That's where this comes from. It takes n squared operations to complete it, n meaning the number of rows. So now you can imagine that as the size of the matrix gets bigger, the cost of processing that matrix grows much faster than the size does. It grows with the square of the size. And that's going to become an important measure of algorithms for the rest of the course. What order is it? And this is called an order of n squared algorithm. Well, if you use that as a reference and sort of print that out and put it in your hip pocket or something, you'll be able to solve the homework problem a little more easily that we're going to have on the next page. What is the cost associated theoretically of doing that algorithm? So you can use the previous example as a base to complete this. These 4's are going to turn into sums, and you can see right away that this won't be a doubly nested sum. This will be a triply nested sum. So do the same thing we did before, looking at where all the floating point operations are, the division, the subtraction, the multiplication, and so forth, and come up with an expression much like we did on the previous page that can be simplified. Using your induction principle, you should be able to prove this formula here as being the sum of the squares of n consecutive integers starting with 1. Prove that first. That's worth 10 points. You'll need that to finish the derivation of the formula, which then is worth an additional 15 points. So there's no MATLAB on this. This is purely a math exercise. Write it up clearly, neatly, and logically, scan it, and turn it in, and that will cover homework 2.2D. Well, I think that's probably enough for one session. So we will take a look at even some more efficiencies next time. Instead of making computations more efficient, we are going to see if we can't make memory usage more efficient. So we'll see you then.